Questions about anything from last time? Well, today I'm going to do this really famous integral, namely that the integral from minus infinity to infinity, what am I saying? Minus infinity to infinity of sine t over t dt. It's hard to believe, but it's pi. That's a famous integral for being conditionally convergent, but not absolutely convergent. And this calculation I'm going to do today also introduces something called Jordan's lemma, which is useful in a lot of contexts. There's two special things that happen with this integral. And if you're going to use residue theorem or something to try to calculate it, you might think I should take the analytic function involved to be sine z over z. But sine z is terribly behaved on that outer circular, the big circle, c sub r. And so you just can't estimate that integral or make any sense out of it. So that's not useful. It turns out that a good choice in this problem is to take the analytic function to be e to the iz over z. Because on the real line, that's related to the trig functions. And so those integrals along L1 and L2 there are going to be the ones we care about. So let me show you how it's going to work. Here's the plan. First, let's figure out that we get something meaningful on the line parts. Of course, let's see. I like to parameterize. L2 is obviously the integral I want. I'm going to take z of t there to be equal to t, as t ranges from epsilon to r. Then I'll very easily get the integral I want, or I see that I get something I want when I write it out, and there the z prime of t would be equal to 1. I'll tell you why I parameterize the left-hand side differently. I want my range to go from epsilon to r. Let's see. No, maybe I don't care about that. Let me show you what I get when I add these two things up. The integral along L1 plus the integral along L2 of e to the iz over z dz is going to be the integral as the t ranges from minus r to minus epsilon, plus the integral as it goes from epsilon to r, and e to the it is cosine t plus I sine t. And we're dividing that by t, and times 1 dt, because the z prime is 1. Okay, this cosine t plus I sine t is e to the it. And now if you think about it, sine is an odd function, and cosine is an even function. And we're dividing it by t, which is an odd function. So, interesting, cosine t over t is odd, and sine t over t is even. That's interesting. That means the odd function, the left-hand side is going to cancel the right-hand side for an odd function. And for the even function, I'm going to get 2 times the integral from epsilon to r. So I claim that this is going to give me something I want. Let's see. The odd function is going to cancel because they're symmetric, and the left side cancels the right side. But the even side is going to get added twice. And so instead of writing it the way I have, I can write it as 2. There's an I in front of it, so it's 2I times the integral from epsilon to r of sine t over t dt. And that's what I want. So there's hope that I'm going to get the integral I want. By the way, something interesting's got to happen here, because if you look at my contour up here again, and my function, f of z is analytic inside and on that curve, simple closed curve. And there's no poles or anything. So Cauchy theorem is going to say the integral around this closed contour is 0. So I certainly don't want to get that the integral is, well, maybe it is 0, but it's not. Okay, so this is part 1 of the plan, is to find out we get something we want along the line there. Part 2 is that the integral around gamma is 0. By Cauchy's theorem. That's an important piece of the business. So I'll call that 2. I'm going to show you that the integral around the circular part of f dz tends to 0 as r goes to infinity. And that's going to use this thing called Jordan's lemma. And the integral around the small circular part, let's see, so we're integrating e to the iz over z. There's a pole at the middle. Okay, now so let me show you how I think about this. This is going to be, it's going clockwise. So, because it's clockwise, it's going to be a minus here. And then we're going to get here 2 pi I, because this is going to be the residue theorem, kind of. And normally, let's see, the residue at 0 of e to the I z over z. Okay, so that's normally what we would get. But this is half a circle. And so in the limit, this is not an equal. This is a tends to as epsilon goes to 0. The big thing here that's new is that I got to multiply this whole mess by a half. It's not a bad mess. And that's because it's a half circle. So this is how I remember what it's going to be. And this turns out to be a useful tool in more general context. Whenever there's a simple pole along the real line, you can punch out a little thing like this and do this routine. I'll explain it later. Okay, so that's what we're going to get for that one. And say that this is how to remember that fact. So here's how to remember. If it was a whole circle, I could use the residue theorem. So, let's say it was a whole circle, minus c sub epsilon about 0. Then I would have the residue theorem minus integral along the whole circle of e to the I z over z dz would be minus 2 pi I, because it's clockwise, times the residue, the whole residue. Because it's a whole circle. And of course we're doing a half circle, so it's a half that. Let's see, what would that residue be? That residue, this is a f of z over g of z situation, and this is a very easy residue to calculate. This residue is e to the I times 0 over 1, which is just one. Okay. And so a half circle is just going to make this half in the limit. Limit as epsilon goes to 0 for the half circle. We're going to get 1/2 times this. Okay, that's the way I like to think about it. By the way, so this residue is just 1, so I get minus 2 pi I here. And so when it's half that, it's just going to be minus pi I. I'll go write that in the box here. This is going to turn out to be minus pi I when I take half of it. Okay, so let's see. I should start showing some of these facts. I've got everything so far. Next thing I need to... Oh, let's see. Let me do the Jordan's lemma part. That was number 3. So let's think about integral along C sub r of e to the I z over z dz. It's tempting to use the basic estimate for integrals. So that would be less than or equal to the max of, let's see, on the circle, I'd get the max of e to the I z over z, and this is over the circle of radius r part. And on that circle, modulus of z is r. And the length of that curve is just pi times r. That's the length of C sub r. And so what's going to turn out to be annoying here, and why this is required a special lemma, is that think about e to the I z. Remember e to the I x plus I y. We've done this before. The modulus of that would be the modulus of e to the I x, which is 1, times e to the minus y, which is the modulus of e to the I x times the modulus of e to the minus y. This one's 1. This one, being a real number, positive, is e to the minus y. So that modulus is e to the minus y. And that's less than or equal to 1, but annoyingly enough, its maximum is 1. So when it was enough just to get that was bounded by 1, we could go places. But now, unfortunately, if you look at that outer curve, when y is equal to 0, we get that the modulus of e to the I z is equal to 1 at these red dots. That's plus and minus r. And so the basic estimate gives us only, so I'll call this an ouch, the basic estimate only yields that the integral around the c sub r part is less than or equal to 1 over r times pi r. And that's just pi. So it doesn't show that it goes to 0. And so that's not going to give us what we need. It doesn't show that the integral goes to 0. We need something bigger. And here's what it is. So I've usually discouraged you to do, if you can use the basic estimate, you should. And so I usually discourage you from doing what I'm about to do. But it's the only way we get what we need. So we need Jordan's lemma. And here's what it is. It has to do with estimating an integral exactly like this. So I'll write, let's see, I'm going to parameterize c sub r by the usual. Z of t equals r e to the it as t ranges from 0 to pi. Then, of course, z prime of t is I r e to the it. And so I need to calculate the integral from 0 to pi. Let's see, the integral along c sub r of e to the I z over z dz would be the integral from 0 to pi e to the r e to the I z t, that looks nasty, divided by r e to the I t, and the z prime of t is I r e to the it dt. Well, at least something cancels there. And I get that that's the integral from 0 to pi. I can pull the IR out front. No, the R's cancel, don't they?
Shouldn't there be an I in that exponent? E, R, E to I, T?
Yes, thank you. There's an I right there. I can pull this I out in front. The R's, those cancel. And then in this nasty looking thing, I'm going to get e to the I, r e to the it is r cosine t plus I r sine t dt. And now let's mess around with that thing. And just like I did in that calculation above, I get an e to the I something. That's going to have modulus 1 when I take the modulus. And then I'll have times e to the minus r sine t. That's equal to 1 at those red dots, but it gets really small on the rest of the curve, and that's going to be the key. I have to estimate this integral more carefully. And so if I take the modulus of this thing, I'd have the modulus of the integral I'm interested in is less than or equal to, and then I would have the integral from 0 to pi. Modulus of I is 1, so I'll put that there, 1. But then I get the modulus of e to the r cosine t times the modulus of e to the minus r sine t dt. And of course this one is 1. And this one, being a positive real number, is itself e to the minus r sine t. And so I get that integral along c sub r is less than or equal to the integral from 0 to pi of e to the minus r sine t. Well, that turns out to be a nasty little integral. You can't find an elementary function that's an antiderivative for that thing. But you can estimate it. And this is what Jordan did in a clever way. Let me show you the picture. I like this picture. Okay, so the picture is I've got the sine function. I'll graph the sine function. Let's say I'm going to have here. I'm going to have to stretch this out. I'll have a sine function going from 0 to pi. That's the graph of sine of theta. I'll make it sine of t maybe. Sine of t maxes out at 1 right here. And now think about what minus r sine theta looks like. Minus r sine theta would be, same, a big bump, but going way down like this. So that's minus, when r is big, that's mostly a gigantic negative thing. At the left and right endpoints, it's 0. Okay. And notice that the sine of t is concave down. That means if I draw this chord here, sine of t is above that. Okay, this is going to pi over 2. Okay, so now I'm going to... So we notice that the thing is symmetric about pi over 2. So notice, 1, this graph is symmetric about pi over 2. So I'm going to take half the integral that I care about to estimate. And this, let's see, what's this? The graph of this purple line here is, what is it? That would be, what's the slope of that thing? It's 2 over pi times t.
1 divided by pi over 2.
Isn't it 2 over pi times t? Yeah. Okay, so here's what I get when I start thinking about estimating stuff. 0 is less than or equal to 2t over pi is less than or equal to sine of t on half the interval, so on 0 to pi over 2. So when I multiply that by minus r, I'd get minus r sine t is less than or equal to minus r 2t over pi, 2 over pi t, and that's less than or equal to 0 on 0 pi over 2. Okay, that's a biggie. That's the thing I want. Interesting, I can't calculate the integral of minus r sine t, but I certainly can of minus r 2 over pi times t, that integral. So consequently, here's what I get. Well, let's see, so number 3, e to the x is increasing. strictly increasing. So I get that e to the minus r sine t is less than or equal to e to the minus 2r over pi times t. And of course, that's less than or equal to e to the 0, which is 1. Okay, now I can do something. So, let's see, the integral from 0 to pi of e to the minus r sine t dt is equal to 2 times the integral from 0 to pi over 2, because it's symmetric. That's because it's symmetric. And now I can estimate that's less than or equal to 2 times the integral from 0 to pi over 2 of e to the minus 2r over pi t dt. And that I can calculate. This is equal to 2 times, let's see, that would be minus pi over 2r e to the minus 2r over pi t evaluated between 0 and pi over 2. Interesting. Let's see, the 2 cancels the 2 in the denominator, and this is equal to, what is it? I can pull the pi over r out in front. And then I get minus e to the minus r plus 1. Minus minus 1. Maybe I should write it like that. Minus a minus 1 when I write it out. And so, exciting news. This is pi over r times 1 minus e to the minus r. And e to the minus r is less than or equal to 1. And it's between 0 and, that's a number between 0 and 1. And so that's less than or equal to 1 over r. I mean, it's less than or equal to, that's less than or equal to 1. So pi over r times 1. And exciting news, that goes to 0 as r goes to infinity. And that's Jordan's lemma. That's exactly Jordan's lemma, that I can estimate that integral by drilling down into the proof of the basic estimate. The integral isn't small at the red dots at the ends, but it sure is small in the middle. Questions about that? Yeah.
So what exactly is Jordan's lemma?
Yeah, I'm going to state it in a minute when I use it again. But it's basically doing this calculation. And this calculation works in more general context. Okay, so the next thing I need to do is the little circle. And that turns out to be not so hard. So next, number 4, I need to do the little circle, and that's, let's see, on minus c sub epsilon, I'll parameterize, let's see, I'll parameterize C sub epsilon. I'll parameterize it as epsilon usual. So this is going to be counterclockwise. Epsilon e to the it as t ranges from 0 to pi. Okay. And now let's see, I'm going to look at this more carefully. E to the iz over z. Here's how I could calculate the residue. E to the iz is 1 plus iz plus 1 over 2 factorial times iz squared plus dot, dot, dot. And we're dividing by z. Now we see the residue. The residue is 1 over z. And then I get plus I squared is minus 1, so that'd be minus 1 over 2 factorial times z, etc. And then I would get plus I over 3 factorial z squared, etc. Next one would be minus something. That has the same radius of convergence as the radius of convergence. Okay, this converges. For the same.
Would it be minus I over 3 factorial?
Would it be? Oh, yes. Thanks. Minus plus. This converges for the same z that the series for e to the iz does. The famous series. And so we've done this before. That means that the radius of convergence is infinite. So that's an entire function. Let's call it h of z. And it's entire. Okay, so this thing I want to mess around with is 1 over z plus an entire function. And by the way, this is the residue right here. That's one way to compute it. Or use my formula about f over g at a simple 0 of g. That's the residue. And so the integral along minus c sub epsilon of e to the iz over z dz would be, excuse me, let's see, that would be minus the integral around c sub epsilon of, I have 1 over z dz, and then I would have minus the integral along c sub epsilon of h of z dz. That one's going to go to 0. Okay, so let's do the first one. The first one I can actually calculate. This one. That one is going to be minus the integral from 0 to pi, 1 over z of t is epsilon e to the it. And the dz would be I epsilon e to the it dt. That is just the epsilon e to the it's cancel, and I'm left with minus I times the integral from 0 to pi dt. That's minus pi I. That's what I predicted this thing was going to be. And I claim that this one's going to go to 0. Okay. And that's because h of z being entire, of course, that's a bounded function in there. And so I'll be done. when I show integral around c sub epsilon h dz tends to 0. And that's easy because if I take the modulus, that would be less than or equal to the max of h on the circle times the length of the circle, semicircle, pi epsilon. And since it's continuous at 0, I can bound that. So h is continuous on the unit disk, on the closed unit disk, so it attains its max there. It attains a max m there. And so this max of h on the c sub epsilon is going to be less than or equal to m. So the max of h on c sub epsilon is less than or equal to m when epsilon is less than or equal to 1. And so sure enough, that goes to 0 as epsilon goes to 0. Okay, so now I can put it all together. Finally, I've got integral along the left plus integral along the right plus integral around c sub r plus integral around c sub minus epsilon. I guess I should put it like this, of f dz, and not residue here, but just a big fat 0 by Cauchy's theorem. This one goes to the integral I want. Let's see, first I'm going to let r go to infinity. That makes this term go away. And then I let epsilon go to 0. That makes this term go away. And after I do that, then this stuff is going to go to the integral I want. I'm sorry, this one doesn't go to 0. This one goes to minus pi I. Otherwise, we're going to get the answer to be 0. But this one goes to 2I times the integral. The epsilon's gone to 0, and the r's gone to infinity. And so this would be the integral I want. And so finally, I get, when I put that on the other side, I get, put the minus pi I on the other side, cancel the 2, cancel the i's, and I get the integral from 0 to infinity, sine t over 2, t, dt is pi over 2. By the way, letting epsilon go to 0 and letting t go to 0 and infinity in that integral isn't a problem because sine of t over t has limit 1 at 0, so it doesn't blow up or anything. It just slides right into what I want it to slide into. And as r goes to infinity, we know that's an alternating series of humps, of decreasing humps. So we know that that also converges. So there's no danger happening as I take those limits to the integral along the straight segments. So we get that. And of course, because sine of t over t is even, the integral from minus infinity to plus infinity would be pi. Because that's an even function. Questions about that? That's a really famous calculation. Okay, so here's a more general version of, got 10 minutes, I can tell you what the more general version of Jordan's lemma. Jordan's lemma is that calculation. And it yields an improvement in our previous theorems when we were trying to calculate Fourier transforms. And so it's if we have P of z and Q of z are polynomials, and usually I wanted the degree of Q to be 2, at least 2 bigger than the degree of Q. But now I can make it be only 1 bigger. Degree of Q is greater than or equal to the degree of P plus 1. And that's instead of 2, which is what I had before. Instead of 2 as before. Then the improved Jordan's lemma, I need to also assume that Q has no zeros on R. On the real line. Then the integral from minus infinity to infinity of e to the I z P of z over Q of z dz is 2 pi I times the residue. It's the same theorem I had earlier. So this would be the residue, I'll call it German A plus for the zeros in the upper half plane. Residue at e to the I z over z over, no, residue at A of e to the I z times P of z over Q of z. Where the A plus thing, German A plus, is the set of zeros of Q in the upper half plane. And so the new twist here is to show that that the integral around C sub r goes to 0. So when you estimate the new twist, estimate e to the I z P of z over Q of z on the circle of radius r like we did. And then we use the basic polynomial estimates. The basic polynomial estimate would give me that P of z over Q of z, let's see, that would be less than or equal to numerator estimate would give me, say, a big A times r to the degree of P plus d of degree of P. And on the bottom, I'd get a little a, a little b. Let's see what I guess, I forget what I like to write. And a b and a little a, r times the degree of q and let's see, that's less than or equal to a constant b over a times 1 over r to the degree of q minus the degree of p. And if I have r bigger than or equal to 1, that's less than or equal to a constant times 1 over r when r big, because that's greater or equal to 1, that thing in the bottom. And so if it was r squared or higher, that would be even smaller. So the biggest that can be would be that when r is bigger than 1 at least. So that in it, that degree of q minus degree of p is greater than or equal to 1. And then we can use the Jordan's lemma to estimate the e to the iz part. I won't write out the details again. Use the Jordan's lemma trick. Method to estimate. You'd have a modulus of e to the iz equals e to the minus r sine t on the circle when you parameterize it. And so it all works out. Another thing that's going to be a general fact that's useful for us. It might happen again sometime soon that we're doing a contour integral, and we're going to cut out a little bump here around a spot that has a pole, and it needs to be a simple pole. And let's see, we're usually going this way along the real line, and this is going to be a little c sub epsilon kind of thing, so this would be a minus c sub epsilon z naught. And this is the real line here. Then the fact is, if f of z has a simple pole, at z naught, then that calculation I did goes through line by line, and so the limit as epsilon goes to 0 of the integral around c sub minus c sub epsilon of f of z dz, it's clockwise, so it's going to be minus 2 pi I times the residue at z naught of f, and then we've got to multiply the whole thing by a half, because it's a half circle. And the proof, if I was going to prove this, it would be exactly the same as I did before. So f of z at a simple pole, you'd get the residue at z naught of f over z plus an h of z, which is analytic near z naught. And so that part you can make go to 0. And so that integral of that part is going to go to 0, and the other one's going to spit out half the thing you get by the residue theorem. So the details are exactly the same.